Uh, Good afternoon, good evening, everyone who has joined in today. It has been a great pleasure to do these sessions with you guys, and we have got brilliant feedbacks on our webinars till now. My name is Ankit Sahu. I'm the co-founder and director of Objective Technologies, and today we have very exciting panel with us uh, from various parts of the AM process chain itself. So we will be discussing more towards the pre and the post AM, enabling the design, and we will be concentrating more on the quality and traceability issues. Previously, we talked about how to be an informed AM buyer. So we had Mr. Ataur Rahman Khan from Scient. We had Dr. Ian Halliday from 3TX 3T AM. He was the CEO of the company. And we also had Mr. Paul from Spare Parts 3D. So we had a brief on an open-ended topic on being an informed AM buyer, and we tried to demystify a lot of questions there on AM itself, and how to buy an AM component, how to invest into the technology, how to start from the process chain itself, what are the pitfalls of the technology itself. So all in all, there has been a great discussion in our previous webinar, which was done a week back on 16th of July. And today we are trying to understand what are the pre-requirement of printing and what are the post-requirement of working. So we will be talking more towards the whole process chain of about the technology itself. So today we have Deepa Srinivasan ma'am, who Dr. Deepa Srinivasan ma'am from Pratt& and Whitney, who is the chief engineer at Pratt& and Whitney, who has vast experience in the AM field. Um, she has had different hats on about the technology itself. She has experienced as a customer also, as an end user also, and as a enabler of the technology even. So again, we have Jingyuan, who is joining us from Dimension Germany, who is the Asia Pacific director. So Dimension is one of the company who deals with the post processing of the polymer components and deals with post finishing and dyeing activity of the same. And we have Mr. Kelvin V from Materialize, who is the Asia Pacific director for Materialize, and he has vast experience on the topic of additive manufacturing, and he has dealt with uh, a lot of customers in this region. And Materialize being one of the premier company to deal in the AM technologies, be it on the pre-processing side, be it on the printing side, and a lot of machine makers work with Materialize to develop their softwares, the firmwares, and Kelvin will throw some light on that topic. So I will be conducting that panel discussion. So today the webinar will be conducted by Mr. Rahul, who will be presenting today. Rahul Pise is the general manager at Objectify Technologies, and he will be initiating the webinar today. Rahul, back to you.
Thanks, Ankit, and welcome all panelists and all attendees. So my name is Rahul Pise. I'm a manager for our metal AM facility, and I ha- had been involved with metal 3D printing for last 8 9 years. And recently, I moved back in India and working with Objectify. Past 1 year had been a very good learning journey for me in metals. My earlier experience was in polymers. So for getting a good quality outcome within your budgets and within your stipulated timelines is very important. And prior planning and how we can think about the quality expectation, and just printing is not the solution. We have to think about prior planning as well as uh, accommodate certain post processes as well. where we can elevate the quality after the printing as well. So sometimes just printed component will not meet your quality expectations. So my role today is to set up a groundwork so that the panel discussion has a certain context as well as the background information for the panelists as well as the audience to keep thought process going on. And the panel discussion, I hope, will be much more effective with the visual feed that I'm going to present today. So let's begin. Okay, so overall quality management has to be concurrent, and concurrent engineering as well as the overall right from ideation to the field duty or end consumer or end user hitting the market. That sort of overall product life cycle management is well established in conventional manufacturing industry. So there are software developers as well as solution provider which help you manage your resources as well as right from ideation to end use, track down how the consumers are using your end products. But in case of 3D printing, that niche is to be served. And as Ankit was mentioning, Objectify had been a kind of a player who deals with 3D printing quite a lot in India, and we spearheaded operations. We acquired unique software solutions, and Ankit was introducing some of the panelists today. So one of them being Materialize, being a very well-known name. So they provide those sort of software solutions to us and wider uh, adopters. So we will take a look at that. But what is that pre-processing and where exactly we should use the software effectively? That's what I'm going to present. And uh, we know that 3D printing is direct digital manufacturing, so that digital data needs to be very robust and the printing can happen as expected. But still, uh, in order to enhance the quality of outcome, just as printed products wouldn't be easily implementable for the field duty or the end consumer use. So that's the reason why we have to focus on certain post-processing aspects as well. So in this visual, I have shared just one representative example. In case of closed impeller that is used in centrifugal pump type of application. So you begin with the how that geometry is. So whatever its complexity is, you study that part. You take a look at the 2D drawings. You do the process planning using Materialize Magics or similar sort of software where machine readable data is to be created out of the computer aided design data. So that's the transition we have to think about. Then we have to do risk assessment, so which is a very crucial role, that where can be process related risk involved or performance related risk involved. How can we mitigate those risks? For that, there has to be certain software solutions which can predict better. That's the pre-processing stage. Once you have thought out what is the construct of a geometry, which is the material that you are going to produce, is it a metal, polymer, or other kind of material? So I'm showing mostly a metal example over here because that's the one that I do every day. So ultimately you do pre-processing and then you allocate the machine. The data needs to be transferred to those machines and the printing occurs. And post printing, we have to do certain specific uh, operations that are dependent on the type of material. So stress relief heat treatment, then we have to detach the support, detach the part from the print plate, and do the finishing via CNC milling if it is essential for certain mating features, and ultimately do the quality inspection via uh, coordinate measuring machines or vernier calipers and gauges. That sort of quality assurance needs to be in place so that last minute there are no hiccups in assembly. So that's how overall importance of pre-processing and post-processing I wanted to emphasize in the first slide itself, because people think that just at a click of a button you get the desired geometry with the digital data. But no, there is a good amount of pre-processing and post-processing we have to take into account. So let's take a look at one by one. So overall quality management system in conventional ways, you might have a practice that you need to assign certain materials, certain skilled manpower or resources of that sort, and certain automated machines. That way, 3M principle they say, man, machines, and materials. But on top of that, in case of digital uh, environment that we are in today, so Industry 4.0, all digitization, that's the norm, and direct digital manufacturing. We have to engage right workflows, right resources in terms of software. So all that is crucial as well. So this is how the pre-processing stage looks like in 4 easy steps. So you need a robust design that can be just a model or certain design iterations for performance or design for manufacturing that you can look for. Data can be forward design, means right from scratch you draft it using computer and modeling softwares, or it can be reverse engineer for the legacy components with the data acquisition via CT scanning or laser scanning. And it can be further optimized as well. So there are certain tools which can assist you to do topology optimization via generative shape design. So that's how the design phase is very robust, and that sort of design, once it is chosen, or how to make those choices, we discussed in our first webinar, which process, which material. Once those choice is made, then you go for the data preparation for converting that design data for 3D printing process. So that is a machine readable translation you have to do. As I mentioned, risk mitigation is important, so we have to do certain process simulations for that sort. And ultimately, this is a layer by layer process. So you do slicing of that digital data CAD models, and you apply a certain process parameter that are allocated, and you can begin printing. So that's how the pre-processing stage looks like. So these are a few examples where we can exploit the power of pre-processing, and better thought process results in a better quality product. So they say, well begin is half done, right? So conformal cooling is one such example where robust design planning can reduce a lot of headache when you are doing actual injection molding. So the parts can come out better quality as well as at a faster rate. Similarly, in case of topology optimization, this is an example of a specific space application bracket where every kg reduced is a additional payload capacity or better fuel efficiency. So that sort of applications are getting popular. So again, in pre-processing stage, there are numerous thought processes going on. The industry is transforming. They are not thinking just one part at a time. How can we consolidate multiple parts? So this is one another space application where they have demonstrated entire engine block for the rocket booster, how they can build it as a single entity with less amount of joints and hassles. So in case of Objectify as well, we had done similar sort of approach for our end users where we built several manifolds or exhaust manifolds for bikes, cars, certain part consolidation that we can assist in product development. That sort of like examples I am showing. So in another area is the lattice structures as well. So how can we lightweight with the lattice structure but still have good amount of strength? So this is an example of a pre-processing stage where softwares like Magix help us optimally orient the part, and support structure is a kind of a waste byproduct. So how can we reduce that? That is the thought process over here. And part traceability is very important in case of 3D printing. In which batch, which quality we could achieve, and what was the material used for which customer, what end use application was desired. So all the part history we have to keep, and this is the way we can have a traceability. And in case of data preparation, we apply those process parameter, but how those reflect in the quality, we have to predict via simulation means. So this is the way we can do process simulation. So we have to mitigate risk and predict the probability of failures. In case there are certain deformations that we predict, or the software is telling that there can be a certain deformation. So how can we compensate for that? That can be enabled using these type of softwares as well. So these are process simulation softwares based on discretized approach, and they predict the load conditions as well as the thermal behavior uh, for the process. So another watch out for 3D printed component is how smooth the surface finish can be. That is dictated mostly by the slicing. So at which layer thickness you are going to process, that choice is very important. As well as over here you can see typical uh, infill for ensuring good dense parts. So how you are exposing energy, be it a laser or any other kind of energy to change the material properties. So how those parameters are to be chosen so that you get a better dense quality part. That is being illustrated with these schematic drawings. So people are taking this to a further level. So in case of our machines, we have just video cameras which are taking snapshots or video feeds for short duration just to monitor the in-process behavior. But people are thinking about how can we take a step further so that with the image processing or process parameter monitoring, how can we monitor and tweak the process during the printing process itself. So that is something as a course correction strategy is being looked at. Now I will talk briefly about polymers as well. So in case of polymer, uh, we have to, just like in metal, do the all sort of pre-processing. But after the printing is complete, for both polymers as well as metals, we need to do post-processing in order to get desired quality parts. So over here, stereolithography or selective laser sintering. So either liquid resin or powder resin. Once the part is printed, we have to detach supports, do the surface treatments via polishing and lacquering, spray painting, or any sort of finish. And in case of UV curable resin, we need to keep it in a curing chambers as well to expose the UV to totally do the polymerization and good quality parts. So that's how the post processing on the polymers looks like. So short blasting, polishing, lacquering, curing. In case of metal, essential step is the heat treatments that dictates the strength of the material. So as the 3D printing process dictates, it is layer upon layer as well as a very focused rapid heating and rapid cooling for phase change of the material. So that's the reason why uh, uh, the properties of the material are anisotropic, and there is a inbuilt residual stress because of the process, just like welding process or something of that sort in case of metals. So we have to do that stress relieving cycle, and why the stress relieving cycle is essential. Uh, we need to do that in order to avoid crack initiations and those sort of failures because of prolonged fatigue and all. Uh, Similarly, how anisotropic properties can lead to that sort of failure, we need to think about that. Anisotropic properties will have a different stiffness or strength in specific orientations, and the behavior under load conditions can be erratic. So that's why we have to make a uniform behavior, and that's why the heat treatments are recommended. And there are as per the material gets different type of heat treatment processes. So we'll discuss that in the panel discussion as well. So I have showed one typical example of titanium alloy grade. So how the strength improves. That is something uh, shown here. So stress versus strain map is shown over here, and with the heat treatment we can improve the directional material. So this is a typical metal post-processing chain. So after the 3D printing is complete, we have to detach the part with wire cut, remove the supports, and after removal of support, there can be a light milling machining for desired dimensions. If there is a threading and tapping essential for fastening, that needs to be done, and then you get a final part that you can do CMM inspections and release for the end use. So this is my last slide. So in a summary, what we discussed today, that we have to have certain prior thoughts with the design data, have a better strategy, then we can simulate virtually and fail virtually. That's better to fail virtually uh, in order to not waste a lot of amount of time as well as the cost associated with the 3D printing processes. So, and that's how we can do a robust process planning in advance. Well begin is half done again. And once that process plan is there, then we can do in-process quality controls via, and that is a easy journey. Once you have a robust plan, robust data to feed to the machines, this is a flexible as well as highly automated process. There is a little chance to intervene in between, and then last mile delivery and quality can be enhanced with certain post processing that is ensured. So with that groundwork, I leave it to Ankit now to take audience and panelists for a brief survey, and later on the panel discussion can begin. Okay, Ankit, over to you. Ankit.
Hi Sankar, can you just pull out the survey for everyone? In the
Yes, yes,
meantime, I'll just start.
I'll bring the survey.
Yes. Thank you, Rahul. Thank you, Rahul, for the great presentation. It was a great thought. So please, on your screen, you can see like three quick questions on like trying to understand what is the thought from you regarding the topic itself, regarding how you perceive the ongoing talk regarding the quality, traceability, and the pre and the post process itself. So can you please, everyone, can you help us vote on this?
So the voting is going on. I'll be running the questions one after the other.
Okay. So the screen is frozen now. So again, like on this topic itself, as we were discussing about um, the pre and the post processing, Rahul mentioned about the requirement of the softwares for the pre data analysis for CAD and orientation and slicing, and also on the post for how to remove from the machine, how to remove the powders, how to remove the resin from the component, and how to post process it for your end application. So he had already mentioned on a lot of discussion points on that. So on those lines, we would be really happy to start the panel discussion. So I would like to introduce Deepa Srinivasan ma'am. She is from Pratt& Whitney. She's the chief engineer for the Pratt& Whitney R&D center in Bangalore, and she has a great experience on the metal additive technologies. And again, I want to introduce to you Jingyuan from Dimension, who is Asia Pacific lead um, for Dimension, who will be speaking a lot about the topic on the topic of post-processing of polymer components. And Kelvin V, who is the Asia Pacific Director for Materialize, who can speak a lot about the pre-processing, DFAM, orientation, support generation, and those kind of topics. So Sanka, is the poll over?
Just 30 more seconds.
30 more seconds. All right. So we will wait for the same. Yes. Sanka, done?
Yes, sir. 10 more seconds.
Okay. Okay. Just waiting. Sorry.
Yes, sir. The polls are done.
Thank you, Sanka. Rahul, can you pull out to the next slide? Deepa ma'am,
Yes.
good afternoon, and thank you for joining us. Ma'am, can I have tried introducing you, but I know I cannot introduce you anymore about your experience in the additive field. So, ma'am, can you help us on your introduction and your thought on the topic?
Sure. Good afternoon, Ankit, and everybody else who's organizing this. It's a pleasure to be back here again. I've seen it the last 4 months, all the webinars, in a stepwise fashion. So congratulations to the Objectify team for doing this service to all of us to enhance our knowledge. You can hear me well?
Yes, ma'am. Yes, ma'am. Loud and clear.
Okay. So good afternoon to everybody here. Yeah, so I worked for about 20 years in gas turbine materials technologies in General Electric in Bangalore in various business units, both in research as well as in development of technologies leading to actually an application. And more recently, in the last 10 years, since 2010-11, I started working in metal additive manufacturing, primarily in powder bed technology, and I would say 50-50 in direct energy deposition and powder bed technology, and little bit, I would say about 10% in electron beam technology as well. So we developed, so with that background, I have a PhD in metallurgy from the Indian Institute of Science, and I've been working on various materials technologies, coatings, welding, joining, brazing, and additive is definitely a prominent one amongst that in the last 10 years. So we developed a number of gas turbine components right from the developmental phase. I won't say the research phase because we used popular powders, but I think one of the main things that we achieved, because it was for the sector of repair and refurbishment of hot section components in both power generation gas turbines as well as aero engines. I think one of the things we did was additive on conventional manufacturing, subtractive manufacturing. If I were to use a punchline, I think that's what we accomplished quite a bit. Hybrid processing, I saw it in one of the slides also. So definitely a topic that Ankit has and the Objective team have identified for me to talk about or discuss is how do you take a manufactured
Rahul,
product.
Can you go to the next slide, Rahul? Yes, ma'am.
Yeah, thanks. Yeah. So how would you go to a sort of designed and manufactured product on the bill plate, starting from the bill plate, and how would you take it all the way to qualification, certification into an application in an accelerated time frame? So I think that is the focus of today's panel, and I'll be very happy to answer any questions from my own practical experience. I currently work in Pratt & Whitney, where again in the aerospace sector, where we haven't yet commenced anything from India yet. We're still in the discussion phase, but United Technologies Corporation, which is now Raytheon Technologies Corporation, has introduced a number of products in not just the gas turbine engine, but in the aircraft related parts, in interiors and seats and in fuel nozzles, pipelines, and so on and so forth. So I'll be happy to answer any questions and discuss how we take an additive part and then how we take it to qualify with repeatability and reproducibility of data. Thank you,
Sure, ma'am.
Ankit.
Thank you, ma'am. Thank you so much. Rahul, can you move? Yes. So again, we have Jingyuan, who's the Asia Pacific director from Dimension. So, Jingy, can you introduce yourself and we can move further?
Yes, hello everybody. First, thank you, Ankit, and thank you to all the organizers for inviting me to be here. And as said, I'm from Dimension, Germany. I'm Chinese. You see the picture. I've been living in Germany for more than 30 years. And career-wise, I have been in the 3D printing industry for more than 8 years. And prior to that, I was in petrochemical industry. I could say that I have been always faithful to chemical industry, because where I was before AM industry, that was plant engineering, and I was in that industry for more than 10 years. And the plant has products like methanol, butadiene, which are also actually the upstream products for the chemicals like PA12, PA11, or TPU. And so coming from petrochemical industry, I go to the 3D printing industry, and we at Dimension, we are world leader for post-processing of plastic 3D printed parts. Yeah, that's all.
So Rahul, can you, yes. So on the next slide, please.
Yeah, okay. So what we are doing with the evolution of 3D printing from prototyping to industrial production, the requirements for 3D printed parts are changing. So what we need for 3D for theory production is that we need high traceability and repeatability, which is more and more important for this new industry. Only with automated post-processing solution, like our solution print to product workflow from us, we together, we can turn 3D printed raw parts into high value products. As Rahul has already illustrated in the first session, that there are different kinds of post-processing steps needed. The parts coming out of the 3D printer, they are still raw parts. And as we are in the new mass production stage, so there are characters which are more important for the final product. We can say one is surface. Surface means the roughness, the glossiness of the part, and water repellentness. They are getting more and more important for serial production for end-use products. And what is more important, that you need color for 3D for the final product. Without color, the part is still a kind of raw part, a kind of prototype. And the importance of color is that color is not just color. Color is part of the company identity. Color is part of the product property. So we are able, with our dimension solution, we are able to give the raw parts the color, the surface, so the raw parts can turn into final products. And we can say we complete the AM value chain.
Mhm. So thank you, Jingy, for explaining about dimension and talking about the topic of post-processing, how necessary it is. So again, like I'll move to Mr. Kelvin. Um, Hi, Kelvin. So Kelvin is a good friend, and we have been working together for a very long time. And um, uh, Materialize being the pioneer of additive manufacturing technology, I would like to introduce you to Mr. Kelvin V. Kelvin, hi, Kelvin. Kelvin, are you there? Hello. So, Mr. Kelvin, I think there's some technical problem. So Mr. Kelvin is the sales director of for Materialize, and he has been handling the Southeast Asia, Australia, New Zealand, and the Korea, India market. He has experience of more than 19 years for various industrial application from Materialize, and he is a bachelor's degree in electronics engineering and an MBA also. So he has been able to enable uh, different customer in different region. So he's one of the leading experience holder of different application of the customer itself. So Rahul, can you move to the next slide? Yes. So 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 Materialize is something like whatever you do before the actual printing of the component. So from data preparation to machine setup to build to heat treatment and post process, Materialize supports you in the whole process chain itself. So a lot of companies who are machine manufacturers look at Materialize as their firmware partner or the software partner. So that is something like Kelvin would be able to speak about it. So Kelvin, can you hear me? No.
Can you hear me now?
Yes, Kelvin. Please.
Okay, sorry, I think there's some some technical problems. Thank you for the kind introduction, Ankit. Couldn't have introduced myself better and on the topic. For those of you who firstly like to thank Ankit and his team for organizing this webinar. I think it's a great initiative, great effort to keep everyone updated. Thank you for inviting me to be part of the panel discussion. Always happy to share my thoughts. So just a bit of introduction of Materialize. We are a largest single site service bureau in Europe. We use 3D printing. Basically, our CEO's vision is to create a better and healthier world. And thus, we started in 1990 with just one machine, a clear lithography machine. And fast forward 30 years, we've got close to 200 machines in our site in Europe. What I'd like to share is also how Materialize is playing a role in terms of software development. So if you look at the slide that's being shown right now, there's a lot of things that's being done before a part can really be printed. And at Materialize, we are involved all the way. One good thing about being part of the largest service bureau is that the people on the floor has so much to complain about in terms of the entire process. And all this feedback is given into our development teams. And then our development teams look at how we can further automate, how we can further make the whole process more efficient. So in terms of what we're doing, we're looking at automation, how you can generate supports automatically, how you can nest parts automatically. We're looking at prevention. We are now developing software that will be able to help you determine what can be printed, how to simulate it. And more important, part of the traceability and also data management. We have an entire process that can track from the minute you receive a file right up to is being printed and shipped. You can trace what machine that part is built on, what kind of post-processing method it's gone through, who handled the files and all that. So we have a variety or a vast experience and capabilities in software development. And I think that the best part about it is that when we develop all our software solutions or the backbone, it's not about developing features that we think is good, but it's about developing features that will really a challenge for the people on the ground. As such, that's why we developed one of the, I think, most comprehensive solution, and that's why we also share this information with our competitors, our customers, our partners, because we feel that when the whole market grows, we will grow together with the market, and therefore we are not stingy, if you want to put it that way, in sharing our knowledge, but we are willing to open it up so that everyone can benefit with the 3D printing technology and work with us to creating a better and healthier world.
Sure. Sure, Kelvin. Thank you for the introduction. I think now we will be showcasing the results before starting the panel discussion from our survey.
Give me a moment.
Sanka, can you? Yes. Yes. So, Rahul, can you move to the next slide, please? So I would like to start with Deepa ma'am on the panel discussion itself. So as ma'am, you had experience as a customer, as a AM part producer, and as a end user of these AM parts. So what are the gaps in the quality side you see, and how should we address, and what are the various ways people should initiate their projects from?
I'm sorry, I lost your voice a little bit.
Yes,
Can you just repeat the second part?
What my point is, like, as you have been on the front side of the table and on the back side of the table, being a customer, being a producer, being a technology adopter. So what are the gaps you have seen as a customer, as a part producer, on the pre side and then the post manufacturing side of AM parts realization now?
Oh, that's well, then that's a topic for a whole day seminar you asked in one question. I mean, it's a huge. It's still, let me talk about. I think people know how to build parts, at least using powder bed fusion now, unless they're very, very complex parts. You're able to build most of the time. Optimization of DFAM and stings with software development, and then orientation is still, people are working on it. There's a lot of things to do. But I think while it is being processed, both I'm using all generically to all the metal additive only. I'm not talking of polymers here. I think each one has its own pros and cons. So as an end user, if you ask me, let me take up this particular part. Why is it not seeing realization as much as it should have in various sectors? Technically speaking, I'm not talking of the financial aspect of productivity, it being a relatively slow process and so on. We're talking of low volume still. We're talking of things which are still, where cost is not going to be penny pinching. But if you look at that technically, if we talk about it, then it is still fraught with a lot of difficulties in terms of defects, microstructural defects, microscopic defects, which we don't have a full handle on. People are working on in situ inspection, in situ monitoring in a production, but it's still not reached that level of maturation remember, casting and all took about 100 years to actually mature the level where we are now able to use casting technology in the last 30-40 years. So additive is, and let for a moment, let's just focus on powder bed fusion, because it looks like most of the people are working on that. So the other important aspect is anisotropy of properties. We know that, so anisotropy in a coupon level, it's okay, you will build along the direction perpendicular, 45 degrees, X, Y, Y, Z, XZ plane, you can do all that. But in an actual part, how do you predict? Because the building of a simple coupon for testing is very different from the parameters, as you mentioned in the presentation, as he mentioned, is very, very different. So how do we guarantee that the variability in the properties are there? And then I'm not even talking about the raw material, which we're also afraid of. We can't even use, we have to use the same heat of powders, the same vendor of powders, the same machine. If you have to really look for a critical qualification. If it's a stationary part, if it is not greatly load bearing, all that is okay. And then whether to hip, whether to hot, isostatically press or not. Conventional wisdom in casting and other conventional manufacturing is you have to do a hip process, especially for critical parts like in the turbines and in space sector. But here, hipping can be a bane. Hipping can actually give a debit to the properties apart from the orientation. And then the whole process of stress relieving is not well understood at all. We need a lot of modeling efforts, lots of R&D. So I think broadly speaking, as I told you, the question you've asked, we can do a 2-day seminar on it. But these are the sort of showstoppers. But nevertheless, on a positive note, let me tell you, based on my experience of qualifying many parts, at least for gas turbines itself, not for the aircraft engine, but for the industrial gas turbine, is that it is doable. It is doable because we do have a huge factor of safety, even in a casting, even in a forging. So all we have to do, that too now with such a huge awareness, lots of people generating data, we need to look at what our requirement is. In terms of, if we don't care about mechanical anisotropy, forget it. If that is a cylinder and a piston in an automotive application requiring a wear test, then we need to do that test at that operating temperature in an accelerated manner and then qualify. So, it's not as bad as it sounds. It's just that the realization it's still fraught with a little bit of apprehension, because a lot of people in any organization, if you're working, a lot of questions need to be answered, and we don't have the answers with data. If I were to actually compare it, it's not as grim as it is, but it's somewhat like the COVID vaccines right now. Some people say August 15th to be introduced. I will say, as a scientist, it's impossible to be introduced in 3 months of qualification. It may well be, but we don't have enough population data to say with confidence that this vaccine is going to work. That is, the Oxford or wherever is going to be or Bharat is going to be the winner. So it's somewhat like that, I would say.
Sure, ma'am. Sure, ma'am. I'll go back to Jingy for the polymer know-how, and it has been like, how do you see you increase the value of an AM printed part in polymers by doing dyeing, vaporizing, and surface polishing? How do you see your end customer perceive that as equivalent to injection molding or something like that?
Thank you for the question. Yes, Ankit. As we are entering we are entering the industrial mass production from prototyping. We are all talking about end use product, end use application. So in comparison with regards to the surface, in comparison to injection molding, we need to focus on 2 aspects. One is the surface and one is the color. The surface means how's the roughness, how's the gloss, how's the water repellentness. in comparison to injection molding. And for the roughness, there are different techniques to get a smoother surface. For example, tumbling, shot peening, chemical smoothing, and coating or galvanization. There are different techniques. We dimension, we focus first on powder beds technologies, which is SLS and MJF. And for these powder beds technologies, the parts are printed layer by layer, and the parts coming out of the printer, they are somewhat rough on the surface. So we need to treat this surface, turn this surface into a better end-use like surface. There are two ways. One is mechanical one, which is a kind of shot peening. We call it polyshot surfacing. And during this process, the part is bombarded with a blasting medium, which compacts the surface and smooth out all the roughnesses. So the result is matte glossy, scratch resistant and dirt resistant surface. There is no material removal, and this process is geometry independent, which means we can treat all the geometries. Certainly, depending on the requirements of the end application, this surface is only matte glossy. If the final application, the end use product, needs injection molding like look, then we have the solution with vapor fuse surfacing. During this vapor fuse surfacing process, the surface of the part is chemically dissolved. We all know that for the polymer parts, the surface has different long chains, and they are dissolved under the vapor under the solvent vapor, and the chains, the chemical chains, they will rearrange, and this results in a more smoother injection molding like look. And this result is also highly glossy, sealed, and washable. So it is also suitable not only for hard plastics like PA11, PA12, it is also suitable for flexible plastics like TPU. And with all these technologies, the AM industry is becoming unviable as an industrial production technology. It's part of the production technology reservoir, I would say, repertoire.
Yes. So like there is one gentleman who's asking like how much time it takes to polish or vaporize a full SLS build, let's say, and what will be the cost for polishing and dyeing if compared to injection molding component itself?
If we do it in vapor fuse, the machine is called Power Fuse S, and this process, the duration of the process is depending on the material and depending on the final requirement for the surface. So it is normally 40 to 120 minutes. And
so
cost.
So the complete SLS build can be taken up.
Yes.
That. Okay.
And
okay.
cost per part, surely it depends how many parts you put it in. If we put in just one part, it would be expensive. And we have a calculation with 200 days of work per year, and depreciation 5 years. And if we have, I think if we have 500 runs per year, we would have 100 pieces in one run, and the whole the final cost per part would be slightly above €1.
Okay, okay. For dyeing and vaporizing itself.
No, just for vapor fuse, just for
Oh,
vapor.
okay.
If it's
Okay.
for
So I,
dyeing, and
Mhm.
it will, I think the cost is almost the same.
Okay, okay. So I think that answers the question of Mr. Vilas Chauhan. So Kelvin, I would come to you on understanding, as Materialize has been the pioneer of AM softwares, and you have one of the biggest service bureaus globally. How do you see Materialize role in the complete process chain from the software's end and pre-processing of the data itself?
Well, thanks for the question, Kit. As I probably shared earlier, I think in my slide that I shared, if you look at it, if you look at the entire, well, chain of the whole EM process, there's data preparation, there's machine setup, there's also the build, there's heat treatment and the resurfacing of plates, and also post-processing. So what we've done is, in our factory, we've actually looked at how we can increase the profitability of a 3D printing factory by optimizing all the process given. And as such, we've actually identified three areas that we can look in terms of software development. The first part is, if you look at the data prep side, the build platform portion, and also the post-processing, quite a few of these steps can be automated. And once we automate all these steps, we can actually reduce manual labor, and we also can optimize the build characteristics. And such automation is key to how we see moving forward. And therefore, in terms of what our solutions have, we've looked at how we can automatically generate support, how we can automatically nest parts for your build, so that you don't have to spend time manually doing this. And once you automate it, not only will it save time, but it also optimizes the materials. It also optimizes the orientation of parts on how you print it. So that's one part. We develop software for automation. And we also look at prevention. As you talked about simulation and all that, when we look at a build platform, we also look at how we can lower crash frequency by ensuring smarter build preparation, how you orientate a part. Or if you want to build a part, before building a part, we run a simulation to see whether that part is printable or not. So that's also an area where Materialize is already in developing. And then the third part of this whole process is also in detection. We've already automated parts, we have prevented parts. But again, Murphy's Law, when things go wrong, everything goes wrong. So if you look at detection is the next important thing. We're also working on solutions where when a part is being printed live, we can already detect potential failures or potential crashes. And then it depends on how the end users or the customer wants to use this information. If you can detect, let's just say on layer 500, there's going to probably be a build failure, then the machine handler can already take that call to say that, okay, shall I take a risk to continue printing or shall I stop? And stopping it earlier would already save you costs in terms of a part if crashes later on in build. Yeah. So we're already looking at all this and putting it in our entire solution to make sure that we can increase the profitability of service bureaus by ensuring that automation, prevention, and detection. So that's where we are looking at.
Hello.
Hello, can you hear me?
Yes, I can hear you. So Kelvin, regarding like the CAD packages and the integration of STLs with the CAD packages, and because a lot of data is lost from conversion from a different background. So it becomes a hurdle in time crunching and all those things on working on the STL itself. So throw some thoughts on that topic itself, like how to work better with STLs, because that's the food for any of the machines itself.
Mhm. That's very interesting. I mean, if you look at it, I'm going to be very honest here. Over the years, we've actually seen CAD packages improve in terms of exporting to STL files. Yep. And if you look at certain big CAD providers, they're really collaborating with us in terms of how they can integrate our solution in the CAD packages that they have, so that you can already sort of like do STL processing in the traditional CAD packages. So yeah, for me, it's like the CAD packages are improving, yes, definitely. But if you really want to have a part that is built well, I think, yeah, designing is one portion, but then you're going to have to look at data preparation of creating supports and or orientating part and all that. So it's probably going to be, I would say, two different playground, where one is about designing, but second one is about optimizing your data to make sure that it is printed well and is printed right.
Sure. Deepa ma'am, I would come back to you regarding how do you see, Deepa ma'am, can you hear me? Hello, Deepa ma'am?
Yes, Ankit, I can hear you. You had muted
Yes,
it.
ma'am.
So.
Yes. So ma'am, regarding the mechanical properties from metal AM produced part to a conventional produced part. So how do you see role of heat treatment, orientation, hot isostatic pressing being like one of the key hot topics in the AM industry currently? How do you see, because as a material scientist and as a uh, process user, so how do you see that being a key trouble for quality assessments?
Yeah, so that's a huge, again, very huge topic. Several PhDs can come out of it. I think so. So, well, again, we don't have to generalize specific to the alloy and the prospective application in mind. I think we have a benchmark in the sense that you would like to use the additive for a replacement of a conventional part or a new design or a new let's say a new application. Then you have to look at the properties. A thumb rule, I would say, from popular alloys that have been out there in the market for the last 6 to 10 years, in powder bed fusion process, at least I would say they can be at best definitely close to that of a cast properties in terms of high temperature creep, fatigue, not just the as built versus stress relieved part. And definitely, because it's a layer by layer casting or a welding process, it can be viewed like that. However, it's not as easy as that, because we do see a lot of examples when we actually try and implement them for the application, that they do not, even though in the as printed part or as per the catalog product, the properties, they don't meet it when you want for a high temperature application, or sometimes they are even they are able to exceed that of a cast part. And the heat treatment that you brought about, in many cases we have seen we are able to tailor the heat treatment to actually have properties between that of cast and wrought, which is fantastic, because you are able to inch towards a forged product through laser or electron beam additive manufacturing. So to answer your question, I mean, it can be both boon and a bane. And with optimization of heat treatment, definitely there are opportunities to improve the mechanical properties. I'm talking of more, fracture toughness, notch sensitivity, stress rupture. I'm talking more advanced properties, fretting, fatigue, and wear, not just a tensile strength at room temperature or high temperature, because it's far more complicated than when you want to, qualify a part for a vane or a blade or a compressor or an impeller or, those kind of applications. So again, to short shrift the qualification process, quickly, within the first week or 10 days, finish the statutory properties and then go on to investigate. Sometimes it can be on the right side, sometimes it can't. So that will close loop into a research area wherein you're trying to understand why is it poor and not sensitivity, why are we not able to move it forward to meet the requirement. So definitely heat treatment plays an important part, not an innovation in that there is ample scope, because metal additive manufacturing is it's a very, very non-equilibrium process. It's a very rapid process. So it does allow for innovative tailoring of the mechanical properties, not just what, as I repeat again, not just what is easily done as a qualification to supply the parts for good apparent density by people such as yourselves who are building lots of parts for various customers. That is the most statutory and the basic requirement. But definitely that is a zeroth step, as you want to qualify parts to reach the kind of maturation level that we need in various sectors. Then we need to evaluate the properties at that suited for that application, and definitely there's ample room to tailor around the heat treatment.
Ma'am, there is one question from a gentleman, Devasish. He's asking, like, it would be very insightful to hear about the aircraft component manufactured through AM and how they have been taking. So we are anyway working with a lot of aerospace companies, but coming from the aerospace company itself, you have already mentioned about some of the components. So can you tell us, like, what are the thoughts from the buying side or from purchaser side itself of these components? How they judge the component itself?
How they
Judge a component when compared to judge. Yes.
I'm sorry, how do they judge the component
On the quality
switch?
side with to switch from a different technology to AM.
Oh, okay. So that is a very, very I would say you can divide it into several bins. So one is definitely eventually, of course, everything is related to the performance of the engine itself. So everything is eventually related to that. But then you can have, as I said, several categories for choosing. I don't know if I understood the question correctly, but you can correct me. So, whether to go from conventional to additive, how do you do the part choosing, and how do you justify, taking into an application? Am I right about the question?
Yes, ma'am. Yes, ma'am.
So yeah, so there are many bins. One is productivity enhancement. So supposing a conventional process is as you know, simplification of processes, simplification of parts. Many of you in this audience know very well about the GE fuel nozzle and many other applications. So one is, so if definitely it's a long drawn process in conventional manufacturing, this is a straight one-step process. So where you can get net shape build. So that is a big driver. So productivity benefits is a big driver. Then if you're not having a large volume, in spares and replacement parts, that is a big driver where you don't need to invest in a lot of qualification time, and you won't even have supply chain to give you low volume, especially for spare parts. So that's a big driver. And of course, design people look at it as a great advantage to accelerate the prototype innovation, in being able to make things and test their design in a very short span of time. So all these are big drivers in the first part of choosing to go from conventional to additive. And I think most know this, These are all, but how do you qualify? How do you get the business case? How do you get internal funding to justify and then to build parts to, that's a lot of money and time, even in the fastest of processes. And I think, and what is a winner there? Some may not be winners. To take off from the previous question that you asked in terms of properties, all the good intentions, we may not be able to meet the requirement in properties one way or the other. I'm not talking again of simple room temperature properties. We're talking of high temperature creep. And this is not very specific to additive also. We've had many other big programs in aircraft engines where people have spent years and years, and then it has not reached where the original intent. So additive is on the same line. It's a fairly recent new technology area in aerospace applications. But coming to the quality part of it, I don't think there can be any compromise. To the best of what we can, as humans, we can do. Apart from that, there are things will fail. There will be things which we don't have control over, many factors control over, and engines will fail and so on. So the quality aspect of it, we have to do the due diligence. We have to give the variability in that property and make sure there are enough builds, especially for an aero engine part, but also for a stationary aircraft part, those are a little bit easier to qualify. Maybe 2-3 builds. You have repeatable, reproducible properties. Then you have the confidence level to draw the statistical variability and introduce in the specifications. Of course, if it is involved Federal Aviation Agency, they have their own metrics, and they will go ASTM
So
standard.
everybody's evolving their own standards how to qualify certain components for certain application for themselves.
Yeah, I mean, it's not that it's so varied, to be honest, Ankit. What do you do? I mean, it's not that varied from organization to organization. There can be secrets about the actual values of, specification limits, whichever physical, mechanical, whatever property, chemical property. I think it's basically you want to know based on the budget and the purse. How many parts will you destructively test? How many will you non-destructively? How many are you willing to accept in a build in terms of productivity as a scrap rate, etc., etc. So I won't say it's very much different from organization to organization, application to application either. It also depends on non-technical ways of and conservatism in the organization.
Sure, ma'am. Ma'am, I'll move back to Kelvin on this. There's a gentleman who's asking on uh, on an end user software Materialize, who's the end user of Materialize software, and the designer, is it that the designer or the part manufacturer itself? So Kelvin, I can answer this, but I would like you to answer this question.
Why don't you go ahead, Ankit, and you give a perfect question, then at least I don't have to say anything.
So Kelvin, I think your software is also on a feedback loop itself. I can totally imagine. So if
Yep.
you want to take it from there for the gentleman.
Yeah. So I think to answer, I think it's yeah. I think most of our end users of the software would be the data prep person or the person handling the machine, not more of the designers. We have designers who use our software, but that's more on creating the lattice structures and patenting or surface textures. So it really depends on what you want to do and what you want to achieve with the software, and that would determine how who actually is the end user of it. Did I get that
Sure.
right?
Yes, totally. So with the software itself, as a user of Materialize, and it has been quite a journey with Materialize in part traceability. So from the start
Mhm.
of the CAD itself till the end of the complete process of a component, we have been using Materialize as a key benchmark. So how that algorithm of traceability works with Materialize?
Well, for us, we've got as part of our data management software, is a solution called Streamix, where it works to provide traceability, where the minute the data prep or the AM department receive a file from the customer or end user, that file is being recorded in the system, and any iterations of that file is traced. And it keeps information like which is the data handler that actually converted the file into STL or did the support generation. And from there, it moves to which machine that it was built on. Not only that, what other parts were built together with that particular part. It gives you traceability of what are the powders that is being used, what batch, so that if there's any recall in future, then you know what other parts to recall. Then from there, it goes to the post-processing portion, where we've really customized our flow, where each and every parts that is being post-processed, there's a tag to it. You know how long and what is being done and who did it. Right to the end, where the logistics or the shipment person clicks the barcode to click send, all those information is being traced. And the wonders of these systems as well, we have a production site in Europe and also in US. We are able to print our parts in US, and we can keep the data with us. So the people in US may not get the STL file. They'll just get the build. They just put it in a machine and they will start printing it. So that also ensures security, so that no unwanted STL parts are released into the open. So because of that, we have looked at the entire ecosystem and designed a solution that ensures traceability. And with Materialize, we are certified, FDA certified, ISO 13485 and all that stuff. We are certified. And all this certification process, if you look at the entire process, part of it is contributed to how we manage the data there. And that's through Streamix.
Exactly. So I'll take closing lines from Jingy, and then I'll move to Deepa ma'am, and then Kelvin. I'll come back to you. So Jingy, any closing line on the topic of post processing? Any final words, as we are just running out of time? So Jingy, can you come back on this?
For me, I think only with pre-process and post-process, the AM technology has future for as part of the to be compatible as conventional technology. So if we talk about printing, we shall not forget pre-process and post-process. And as Kevin has already said, post-process can be shall also be traceable together with the printing job, traceable and repeatable.
Exactly. Yes. So Deepa ma'am, any closing words from your end on the topic itself?
Yeah, well, thanks for organizing this. And but as I said before, I would, although there are a lot of uncertainties in, taking this to fruition in a short time, but it's not as difficult or scary as it sounds. People are taking lots and lots of parts. Sometimes they won't talk about it. So whoever is interested, definitely, we should do the experiment to take it forward. I would say a very good success rate if you know the initial benchmarking, and to be able to take it as far as the post processing, the properties, and being able to qualify the part.
Exactly, ma'am.
Thanks,
exactly,
Ankit.
ma'am. Thank you, ma'am. Thank you.
Yeah.
Thank you, ma'am. Kelvin, can you please help me with your closing words on the topic itself? I'm not able to
Sorry,
hear you,
yeah.
Kelvin.
Looking for the mute and unmute button.
Yes, Kelvin.
Yeah, for me, I think if you look at it, there's so much in additive manufacturing that can play a role everywhere, and I think additive manufacturing can benefit everyone. And I think everyone has to know what they want before making a decision. And I think that is the most important part. I mean, to know what you want before going to do what you want to do.
Yes. Thank you, Kelvin, for your words. Thank you, Jingy, for joining us. So I would like to announce our next webinar, which will be on 30th of July, 4 p.m. So Mr. Dilip Mendes, who's the managing director of 3D Systems, Mr. Dr. Kumar Kandaswamy from Enabled Engineering. He has been a material scientist himself, and Dr. Dipankar Banerjee from ISC. He's the professor and one of the Padam Shri awardee from materials. So he'll be joining us. And thank you everyone for joining. Thank you, Deepa ma'am. Thank you, Jingy. Thank you, Kelvin, for joining us on such a short notice. And it was a pleasure hosting you guys. See you next week. Thank you. Thank you so much.
Thank you.
Thank you. Bye-bye.
Thank you.
Bye-bye.
Bye-bye.